Welcome back. In this lesson we'll see the basics of measurement system analysis that is used for variable data. Measurement system analysis is of two types: attribute and variable. As we know the types of data, depending on the type, we perform the analysis. For example, data like pass, fail, go, no go, customer service rating. These are attribute type of data. So we need to make use of the attribute MSA. While the data that is continuous or discrete variable, that should be analyzed with the help of variable MSA. Variable MSA can be classified into three types: crossed, nested and expanded. These types are named based on the design that is prepared for data collection. In crossed R and R, the same parts are measured by each operator many times, while nested R and R is used when the part under test is destroyed, and because of that, only one operator can measure it. This type of R and R analysis assumes that the parts within a single batch are identical enough to claim they are same. In expanded R and R, one or more following condition exist. When there are more than two factors, operators, device and parts, in case when the factors are both crossed and nested, in case of an unbalanced design, or in case of random factors. As we know that the variability of measured observations depends on inherent process variation and measurement variation, we can denote it with the help of this equation. Sigma m square is equal to sigma square plus sigma e square. Here, sigma m square is the variance of measured observations, sigma square is true process variance, and sigma e square is the variance of measurement errors. Sigma e square can be calculated by adding sigma t square and sigma p square, the variance in repeatability and reproducibility of observations, respectively. We can thus represent the gauge R and R as the following equations. Here are the guidelines laid down by Automotive Industry Action Group, which are generally referred to, though an organization may have different guidelines based on their past experience and industry type. If the measurement system's variation is less than 10% of processor's variation, then it is acceptable. Similarly, tolerance should be less than 10% and percent contribution should be less than 1%. Number of distinct categories should be greater than 10. We'll go through these guidelines again when we will make conclusions in our coming example. In Sigma Excel, the ANOVA table values are utilized to calculate percent contribution and standard deviation. To calculate percent study variation and percent tolerance, we need to know values for the standard deviation and tolerance ranges. Sigma Excel defaults to a value of 6, the number of standard deviations within which about 99.7% of the values should fall. Tolerance ranges are based on process tolerance and are business values specific to each process. Let us see what are the steps of doing measurement system analysis. First, we select parts for the study across the range of interest. Then, operators or inspectors or equipment, as appropriate, are selected. An important point here is that the inspectors must know the purpose of the analysis and that the inspection system is being evaluated, not the people. After selecting the operator, we calibrate the gauge or gauges for the study. We need to consider and evaluate linearity, stability and bias at this point. Once the system is calibrated, the first operator measures all the samples once, in random order. Then second operator measures all the samples in random order. This process is continued till all the operators have measured all the parts one time. This completes the first replicate. We can repeat the steps 4 and 5 for the required number of replicates while ensuring that there is always a delay between the first and second inspection. Once all the measurements are done, the data is entered into analysis tools to analyze the results and draw conclusions. So, as we just saw, the first step is to allocate parts for MSA. Let us see now how we can do that. As we know, the MSA study is designed in crossed or nested way. We will learn about a 10 by 3 by 2 cross-design, where we'll pick 10 parts from the population. 3 operators will measure them, and for each part 2 trials are run. In total, 60 measurements are taken in this design. Here are the steps to create data collection sheet in Sigma Excel. This is for variable MSA. Go to Measurement System Analysis, create Gauge R&R Crossed Worksheet. Since we want a 10 by 3 by 2 design, we will have to put the numbers in this pop-up and click OK. It will generate a worksheet which will have details in form of randomized parts and operators. Measurements are registered against each of the combination as given in the sheet. Once data is prepared, go to Measurement System Analysis again, select Analyze Gauge R&R, Crossed, and select the data. In the dialog box, select the headers for part, operator and measurement. The standard deviation multiplier is put as 6 here, as Sigma Excel takes it as a default value which is used in process capability. However, we can choose 5.15 as multiplier, which is common in automotive industry. This is the summary that we get in Sigma Excel. The first table shows the inputs that we have used in this example. Process tolerance, standard deviation multiplier, alpha to remove interaction between parts and operators, confidence level, etc. The second table shows the analysis of variance for part and operator interaction effect. We can see here that there is no interaction effect between operator and parts, as p-value is more than 0.1. This means that the part measurements have no influence of changing operators, though there is a significant variation in parts itself. The variance component shown in the table represents the contribution of variation to the total variation of the study. Percentage contribution is based on the variance components, and is calculated by dividing each value in variance component column by total variation and then multiplying the result by 100. Study variance is calculated as 6 times the standard deviation for each source. Percentage study variance is used to compare the measurement system variation with the total variation. We should also note, as a generic guideline, the percent total variation should be less than 10% for a measurement system to be acceptable. There are also the tables for percentage tolerance in number of distinct categories. Sigma Excel calculates percent tolerance if process tolerance is entered, like in this example we have given process tolerance as 16. The percent tolerance compares the measurement system variation to customer specification limits. As a generic guideline, it should be less than 10%. The number of distinct categories should be at least 5. It is calculated by dividing part variation with gauge R&R and multiplying the resultant with a constant 1.41. Now, we will match the values with the guidelines laid down by Automotive Industry Action Group, which are generally referred to. Though we should again note that an organization may have different guidelines based on their past experience and industry type. The measurement system's variation is not less than 10% of processor's variation, and thus it is unacceptable. Similarly, tolerance should be less than 10% and percent contribution should be less than 1%, which again is not the case. Number of distinct categories should be greater than 10, while here in the example it is just 3.5. We can conclude here that the current measurement system is not acceptable. Let us also have a look at the graphical output that we get during MSA. Here is the art chart, and it consists of the following. The plotted points are the difference between the largest and smallest measurements on each part for each operator. If the measurements are the same, then the range will be equal to 0. The center line is the ground average for the process. The control limits represent the amount of variation expected for the subgroup ranges. These limits are calculated using the variation within subgroups. If any of the points on the graph go above the upper control limit, then that operator is having problems consistently measuring parts. The upper control limit value considers the number of measurements by an operator on a part, and the variability between parts. If the operators are measuring consistently, these ranges should be small relative to the data, and the points should stay in control. In this example, though, we can see that operator 2 has inconsistency. Now, the X-bar chart. This chart compares part-to-part variation to repeatability. The plotted points are the average measurement on each part for each operator. Center line is overall average for all parts by all operators. The control limits are based on the variability between parts and the number of measurements in each average. And since the parts chosen for a gauge R&R study should represent the entire range of possible parts, this graph should ideally show a lack of control. As we can see here, many points are above the upper control limit and below the lower control limit. We can say that there is no control here. We can conclude with the help of the analysis that this is an unacceptable measurement system. In a good measurement system, the largest component of variation is part-to-part variation, while, if a large amount is due to gauge R&R, the corrective actions are needed. The components of variation can be visualized with the help of this chart. In Sigma Excel, the variation is broken down in specific sources. The same can be represented in the form of clustered column bar in MS Excel. Like in this example here, we have manually created this chart using the table on gauge R&R metrics. Another column is added for percent total variation, and the same is calculated by dividing each variance component from total variation, and multiplying the resultant with 100. Here if we see, part variation is high, though gauge variation is also significant. And as we have been concluding so far, here also, we can quickly see and conclude that the measurement system is not acceptable. The Sigma Excel output also has Multivari charts, which show each part as a separate graph. Each operator's response readings are denoted as a vertical line with the top tick corresponding to the maximum value, bottom tick is the minimum and the middle tick is the mean. The horizontal line is the overall average for each part. These graphs can help us in quickly identifying where the variation is lying. So, with the help of this whole study, we have concluded that the current measurement system is not acceptable. In such cases, we have to go back to the root causes behind, and take corrective actions. Once corrective actions are taken, study is again performed. We should understand the importance of MSA. Well, unless we have a robust measurement system, we cannot trust the data and eventually the fact-based decisions that we are making. Let us do some exercises. In the workbook you'll find the data on sheet 2.3.4. Perform the gauge R&R study and interpret the results. Now we will move to the next lesson. Here we come to an end to this lesson. Should you need any support, feel free to contact us. Thanks for watching this video, and see you in the next lesson.